And I only want to show you one of these. We haven't published anything yet because we still would like to do some bioscreening here, and we are limited there. It was this analgesic compound. It was known in a patent that these compounds here had a better performance than pro-cocaine, for example. And when you look at this is what we can generate photochemically. You can easily kick out water because of conjugation here. And then with a nucleophilic substitution reaction, you can introduce here, this is first year chemistry, the amino function. We did that with this brominated compound, and that was the first surprise. If we do that in acetone water, you end up with this mixture. This is what we want to have. But this is what we got at least in 50%, and it was difficult to separate the two. This is a very interesting molecule, but unfortunately it's a dead end in this project. There's a nucleophilic substitution, of course, happening here during the mechanism of the photoreaction. And we were able to control that. Again, know your chemistry. The other product that we form is potassium hydroxide, a very strong base. So when we buffered the formation of potassium hydroxide, we were able to completely annihilate this undesired reaction. So we did the reaction now in pH 7 buffer. We got in very large amounts and in very nice purity this precursor, and then with a little bit of acid and diethylamine, you get the final product. Very nice. And then we went big again. Not so big as with the outdoor chemistry, but big. Because Professor Griesbeck then bought this excimer lamp. It's like Darth Vader's lightsaber, so obviously he took it off him and he put it into this glass vessel. And we now scaled up our photodecarboxylation to up to 40 grams, which is quite a scale for a photochemical reaction. The reaction can be done in water, which is an advantage, because the potassium salts are soluble in water, whereas the products are insoluble and they precipitate. And they get accumulated down here in this reservoir, whereas the rest of the solution is pumped up again through this side arm, passes by the lamp like a waterfall, and you have the leftover starting material reacting. Very nice thing. And because you're working in water, you can not only use GC to trace starting material and product, you can also monitor the pH, because the other product is potassium hydroxide. And here we are not buffering. So the pH increases during the reaction, you reach a plateau. And everybody has a pH electrode, not everybody has a GC, but everybody has a pH electrode somewhere. And when you reach that plateau, you know the reaction is finished. And then you can do the workup. And the yields were quite nice. So here are the 6 reactions that we studied. I have the amount somewhere here. So it's from 6.5 grams to 36.7 grams of starting materials. And also the products then are in the same ranges. So obviously it's quite a nice way to make at least demonstration scale reactions possible. All right? Okay. That was my PhD. And beyond that. And then in DCU and also in JCU, I became more interested in outdoor stuff. And there, in particular in JCU, it's a very sunny location. We have 300 days of sunshine a year. Last year was a bit tricky, but a very sunny location. So it's a perfect location to bring back photochemistry where it came from, outdoors. And here's a picture again of this Profis reactor, and you can tell by the color already that we obviously use some dyes here. And the chemistry that we're doing are photooxygenations. So they involve singlet oxygen. Unfortunately, as a scientist, fortunately as a human being, you cannot do any chemistry outside. In particular, the ketone chemistry and the cis-trans isomerizations you can do. But if you look at the solar spectrum, you can work with dyes. They absorb very nicely in the visible, that's why they're colored. And photooxygenations with these sensitizers like Rose Bengard fit perfectly into the solar spectrum. So they make absolute sense also economically. And the reactions that we studied here are making of a quinone again, and making of a precursor towards a fragrance which is industrially used. So this is an industrial process, and we can do that with the help of Mother Nature outside in Australia. Well, singlet oxygen. It's quite a name, but if I ask you to draw the structure of oxygen that we breathe, you will probably, half of you will draw it this way, which is wrong. And the cosmetic industry likes to scare us of free radicals. That's also wrong, because we're depending on one, and that is this one. We are breathing a biradical. Oxygen is a biradical. And the double bond version of it is a higher energy version of it, which is extremely reactive. And you need only 22.5 kilocalories to convert triplet oxygen into singlet oxygen. And you do that with the help of these colored compounds, these sensitizers or dyes. They take on the light, and then they transfer that energy onto oxygen, and you're getting from triplet to singlet. And these are the typical dyes that you work with: methylene blue, rose bengal. There's some data here where they absorb and how efficiently they do this process. Well, it's more for the, and you can immobilize them also, so you can recover them. But we think that still the soluble version of it is the best thing. There's a disadvantage of singlet oxygen, that's a lifetime. It likes to exist for quite some time in halogenated solvents, but they are not very green. They're actually quite hazardous. We typically work in alcohols, and we have 7 microseconds. So this is the lifetime of this species up here, now to bring a reagent there and to make a photochemical reaction happening. But time is sometimes money, but not always. So when you're working outdoor, actually, you have some time. So it's not so much of a big deal. And we did it with just bringing the apparatus outside instead of doing it indoors. We brought it outside, and the picture from Dublin actually. So in Dublin, which is not the sunniest location, we did solar chemistry, and we synthesized these new quinones here, published that in Green Chemistry. We synthesized some classical compounds like ascaridol, and we also synthesized very efficiently in Ireland with Irish sunlight fragrance precursors. So relevant reactions. In Australia, we're currently beefing that up a little bit, so we are trying to grow, because I'm dreaming of a solar production plant for perfumes in Australia, trying to convince the university, but they're always stubborn people anywhere in every university administration. So what we do is we have this flatbed, which is nothing else but a modified window. You can now do reactions on 10-liter scales, so already not so bad. And citronellol, alpha-terpenine, and beta-pinene are converted very rapidly on quite large scales in fairly short times into valuable chemicals. Okay, and the isolated yields are not bad. The beta-pinene reaction is a bit slow, but all the others are very fast processes. So nice. And then again, this is although a few years back, we went very big, and we made this relevant process outdoor in Cologne again. And 8 or 6 liters of citronellol were converted in very short time during very sunny periods of time, and the yields are given somewhere. So this is the mixture that you're getting after in situ reduction that you can do in the solar reactor. You get these 2 regioisomers, and this one here is then cyclized again in the solar reactor. So you use now solar heat instead of solar photons, and you can convert citronellol in 54% yield based on the important regioisomer, or in 99% yield based on the whole mixture, or based on the regioisomer, sorry. 54 on the 2 isomers, 99 on the single one, into the rose oxide, into the perfume. And this reaction was actually performed by Dragoko, a perfume industry company in Germany, when they had problems with their production. And here's just the disappearance of the starting material. So after 1.5 hours here, the starting material was gone. You're not monitoring the products because you have actually 3 products, so it's quite a complicated reaction. And in the GC, you get also things like eliminations happening, so you just monitor the disappearance of the starting material, and you're fine. And now we went small. So we started micro photochemistry or micro flow photochemistry in DCU and JCU. And this is our new toy, still in Dublin. It's a twin tower that uses a microcapillary, 5 each, And this reactor now allows you to do small libraries of 10 different compounds using a 10 syringe pump. And you can collect then here 10 different or 10 times the same reaction mixture in these flasks, while you irradiate them on these 2 individual towers. Every tower has about 10 meters of a microcapillary, and micro is only the dimension of your vessel. It's not the whole thing itself. And the whole thing is, and it's another advantage, very cheap. The most expensive part of that, that's 3,500 euros. This is pretty much made out of scratch. So the whole thing probably 5,000 euro. So very simple. Now why microphotochemistry? I went to a conference a couple of years ago and I was presenting on our solar work and I said, big is beautiful. We need to go bigger. And then I saw a poster on microphotochemistry, and when I started a discussion with that lady, I thought, well, that's a toy. It's a toy. But that's it. But microreactors actually have some very interesting properties, in particular for photochemical reaction. And the most important one is they have very thin layers. Why is that important to photochemistry? Because we are slaves of the Beer's law, the Beer-Lambert's law, that determines, if you like, if you do a photochemical reaction, the concentration is important of your mixture, of your chromophore, but also the path length. And path length is exactly the width of your microchannel, or the depth, excuse me. So if you have a very, very small, narrow container, a shallow container, your L here, the path length, is becoming neglectable. And that means you can work on quite high concentrations now instead of the usual high dilutions you're working with. You also work flow-through, and that means you are removing the product mixture from the reactor. And as such, you can protect now the product from reacting any further. Sometimes the product is still photoactive, and you have to get it out of the light into the dark, and by doing it flow-through, you can do that very easily. If you work in batch, you can do that. You can also do automation and scale up, and New Senses Group has demonstrated that very nicely. You work on small scales. That makes it attractive for green chemistry, but it makes it in particular attractive as a research tool. I told you earlier that you need less than 10 milligrams these days to do ultra high throughput screening. And these things here, if you sell them in a set, are delivering exactly that. And now industry may actually have a tool to try out photochemistry, which is always this very exotic piece of equipment. This thing is not exotic really. Just looks like a floppy drive a little bit, an external one. And you can use LEDs, so small reactor plus small light sources. They are considered energy and cost efficient. They also have more narrow wavelengths. And fortunately, and that is very interesting, microphotochemistry has reached industry. This is a picture of a production plant in Germany where they use these microreactors to produce a precursor to a new anti-cancer compound. And the photochemical reaction is this one down here, a very unusual one. You go from an N oxide and you get a hydroxylation here at the aromatic ring. Okay, it's a photochemically stimulated reaction. And the target molecule, or the starting point, was this natural product here. So this is the photochemical reaction that is done in this reactor, and what you see here is, this is the lamp. This is not the microreactor. The microreactor is this piece of glass. So the fellows here are producing a very thin film. It goes in from the top, they create a very thin film like a waterfall, and it passes by the lamp and then goes out there. And they compared it with the conventional reaction. So when you do that in batch, your conversion is 85%, 50% isolated yield, and you have to work with 0.1 concentration of the starting material. If you do that in the microreactor, your conversion is higher, your yield is much higher, and you can work 6 times the concentration. So what I said earlier about the Beer-Lambert law is indeed true here. And they patented this process, and they are producing here, at 2 kilograms of this precursor a day. 2 kilograms, and that is obviously the dimension we have to think in. We cannot produce 100,000 tons, but we can produce small volume chemicals like this one. All right?